happy to brief about Dr. Deepak Mishra, today's speaker. Dr. Deepak Mishra is Scientist, Engineer SG and Head of Navigation Payload Electronic Division at Space Application Center, Indian Space Research Organization, ISRO, Ahmedabad, and he has received PhD degree from IIT Banaras Hindu University on topic Joint Source Channel Coding for Deep Space Applications in the year 2012. He received his MTech degree in Communication Systems from the Department of Electronics Engineering, IIT BHU in 2003 and BE degree in ECE from Government GB Pant Engineering College, Uttarakhand. He is associated with SAC ISRO since the year 2003. During his tenure, he has been involved in various subsystems development of various ISRO projects. Currently, he is involved in the design and development of payload for NAVIC systems as an associate project director in technology demonstration payload and as a focal person communication module for Gaganyaan project. He has more than 65 papers in various international journals and conferences. He has also delivered invited talk in international conference at Tokyo University, Japan in 2016. He has 4 patents and 3 copyrights to his credit. He is the focal person for signal processing module of postgraduate course of United Nations SATCOM course and faculty member in navigation systems course. He is a fellow of various academic institutions like IETE, IEI, ASI and ISSE. He is appointed in the board of advisory members of MathWorks India. He is also an ISO 17024-2012 certified project manager. He is approved PhD guide at IISc Bangalore, IIT Gandhinagar, Gujarat University and Nirma University, Ahmedabad. And currently 4 PhD candidates are working with him. We are proud to have you with us today, sir. And I welcome Dr. Deepak Mishra to give a talk today.
First of all, I like to thank Professor Chandrasekhar, Osmania University, for inviting me for this workshop to deliver my talk. We'll go some basic slide and then directly we'll come on the system design aspect and how we do our verification in the design, how we do the validation in the design. We'll come later on. So I will try to build up slowly so that it cannot directly go into the design and start discussing the design. If you see the flexibility versus the speed, there are 3 major pillars for the space design. One is called processor based design, another called FPGA based design, another called ASIC based design. Typically, we preferred FPGA based design. The reason behind is we required a fast turnaround time. If you go with the ASIC cycle, it will take a lot of amount of time and sometime we do not have such a big volume. It's satellite to satellite, some design change is there. So, we typically preferred FPGA based design. But although sometimes what happens once your design is such that we have to replicate in multiple satellite like NAVIC type of satellite, it's a replica of satellites only. So, there we preferred some ASIC based design also. Where some mathematical computation is required, then we preferred a processor based design also. But there is a compromise. What is the compromise is speed versus the flexibility. So, ultimately we required not a very huge flexibility, but at the same time some flexibility we required in the design. That is why we preferred FPGA based design. So, as you see the trend of current FPGA based designs, basically they are market driven. You can see that initial FPGAs are 180 nanometers. Nowadays, if you talk me advanced, whatever I am talking is now for the space qualified FPGAs. So, currently if you ask me, the current space qualified FPGAs are 28 nanometers and latest devices is like RTG4 from Microsemi, Vertex 5 from Xilinx, and now the RTG4 is coming with the polar fire, RT polar fire they can say. So, all these are 28 nanometer based design and they have a very efficiency in terms of reliability. So, not only in India we are using these devices, like European Space Agency, ESA, even NASA, they are using these devices. So, they have a very good heritage. See, in the space business, one thing is also play a role is the device history. So, suppose we are selecting any device and once the vendor says this device has been flown in 10 NASA satellite missions of GEO, then it's our confidence level will be slightly higher side, that reliability is proven. So the reliabilities also play a very big role in case of space business. Flexibility also we want. So earlier what happens, if you see the FPGA devices, even in the commercial domain, they have a simply gate logics, nothing is there. But nowadays, if you see the FPGA devices, they are coming with lot of flexibility in terms of PLLs, they have a DSP chips and inside itself, they have now we can put very well soft processor inside. So that way now the flexibility is increased inside the FPGA. And then the low development cost, whatever every FPGA vendor nowadays releasing lot of IPs where we can use it for your applications. So like Xilinx, Microsemi, they have a now very big pool of libraries where you can use them to develop your own design, okay. So that's why the FPGA is there. So as I mentioned, nowadays if you see so many things are there inside a single FPGA, any big FPGA you named it, either RTG4 or anything. You can see that they have a, like in routing side, they have a low cost CLBs, vector routings, embedded multiplier, DSP blocks. Similarly for the system memory, they have a block memory, distributed memory, external memory, clock management units are there, PLLs are there. So this basically is required for any big design. Any signal processing or VLS design if you want do in satellite communication, you require all this tool. And in a single FPGA nutshell, we are getting all these things. So that's why we are now migrating towards mostly towards the FPGA design. Now in terms of technology, if you ask me, there are three major technology nowadays in the market, if you see the FPGA market, that is called SRAM based, flash based and anti-fuse based technology. The most reliable FPGA nowadays is anti-fuse. As you know, the name itself is suggest, once you program the FPGA, the logic cannot be changed. So this reliability is enormous, but they have very less flexibility. And suppose by any means some bug is there on board, you cannot reprogram it. So it's a basically you have to decide where, so typically where the control applications are there in onboard satellite design, where we prefer this anti-fuse technology, where we are rest assured that it's not going to change with respect to time. But where we required some flexibility, some reprogrammability on board itself, then we go for either SRAM or flash based technology. So Xilinx FPGA mostly if you deal with, they are mostly SRAM based, and Microsemi, like I mentioned RTG4, they are basically flash based devices are there. So each have some pros and cons, and based upon your application and mission profile is also very big role to play. Where we are launching the device, suppose you are going for the GEO mission, then reliability will ultimate is there. But suppose you are going with the LEO missions, LEO satellite orbits, then you can go with the SRAM based device also, there is no issue, because SRAM based device typically quite big in nature. So in the single FPGA itself, you can sit with lot of applications. So this is just I am comparing as a what are the pros and cons of each technology. So as I mentioned that reprogrammability is the good part of SRAM and this flash based. Anti-fuse didn't have a reprogrammability capability, but if you go with some other options like external configuration file, instant on IP security, so each has some basically pros and cons, some are having, some didn't have. So based on our project requirement, like Chandrayaan 4 type of mission or Chandrayaan 3 missions, where we have gone with the anti-fuse type of technology, where the reliability is the most aspect, we cannot afford any failure there. So, but some applications where we required most DSP blocks, so there we got in SRAM based technology. So we have to go with Vertex 5 or some other devices. Basically we do SDL programming in order to do fuse the logic in FPGA. We do have to do that. We typically use both Verilog and VSDL for programming the FPGA. So these two standard languages we are using for right now. I think this is quite adaptable now even in the commercial market. So both we are using very frequently. Apart from that, there are some mathematical computing applications in onboard where we require a DSP processor also. So basically if you ask me what is so specific about the DSP processor, so they are required where we required a lot of mathematical computation, like suppose onboard you have required of FFT calculations. Suppose you are required to do lot of digital filtering. So there we have a dedicated processor sitting, although there we have now two options on board. One is either we have put a dedicated DSP processor chip inside our design, or we can place a soft processor itself inside the FPGA. But the problem with the soft processor, it will occupy some part of your FPGA, and suppose your logic is big, we cannot sit processor together with the FPGA, then we don't have any other option to go with the dedicated DSP chip inside our design to go for the applications. Although we preferred soft processor because then our design is quite simple. But suppose we have putting the DSP processor with the FPGA, then synchronization of both the ICs and all the logics, control logics has to be played. So then it's slightly complex in design, and the thumb rule for the onboard design is your design should be as simple as possible. So we always try to put a single FPGA based design, because then my design is simple, but the challenge is, if suppose what happens once your design is not fitting in the single FPGA, then we don't have any other option. So that is where DSP we choose. Typically, if you ask me about the architecture, typically two architecture based DSP processor are available. One is called von Neumann and another is called hardware architecture. Hardware architecture basically separate program memory and data memory is there for the processor. And if you ask me the current state of the art DSP processors, so basically there are two important aspects for the DSP processor. One is called single instruction multiple data. In a single instruction, like you want to do the add operations for the array of the data, you give single instruction, all the array of data will be getting added. So that is called a single instruction multiple data, means a single instruction will do n number of operations in a single cycle itself. Second thing is the very long instruction word, where instruction level parallelism you do, means a single instruction having a lot of small instruction set. Like in this case, that if you see in the single instruction, one addition, one division, one multiplication and one. So in a single instruction you can do multiple operations together. So these are the two things where all advanced DSP processor are sitting. So if you ask me about the architecture wise, they have both VLWI and SIMD architecture, although deep pipelining is also nowadays has been happening in the DSP processor. But the problem with this type of processor is they are very power hungry. So you have to basically select. You cannot directly select any advanced DSP processor, because onboard design is basically is the power constraint as well. You cannot have an infinite power, because all the power we are getting from the satellite is from the solar panel, and solar panel has a limited power generation capacity. Okay, so based on our application, we try to use the minimum DSP processor we can meet, not the maximum. So that is the design difference, where if in ground, if you are trying to design something, we will use the best processor which is available in the market, but in the space business we are selecting the which can meet the minimum requirement of our design, not the maximum. So that is the design difference between them. Now coming to, I will just showcase you some cases. So in terms of satellite design, we have 4 types of satellites in ISRO. One is called communication satellite, another is called a navigation satellite, third is called a remote sensing satellite. Remote sensing satellite also classify in 2 domains. One is called optical satellites, another is called microwave domain satellites. So I will try to showcase each one of them and what technology which we are using in each satellite design, that also I will try to show you. So if you see early days, once ISRO has just started in 1960s, when Sarabhai has started the Indian space program, we have a very analog architecture satellite design. Typically it's like we have some uplink frequency, and then we just do the frequency translation at onboard, and the data, and then we have a downlink frequency. And this type of scenarios is there in 80s, where the Doordarshan is coming into the picture, where one channel is broadcast across the India, and everybody has a Yagi antenna, and they can tune it to the satellite and they can see the Doordarshan channels. Okay? So that is the classical analog architecture. But nowadays, as you see that there is a famous dialogue, "Ye dil mange more." So now they are asking, in the single satellite we want n number of applications. Okay? So, but and the problem is we don't have such a advanced onboard power generation system. So within the limited capacity, we have to cater a lot of applications them together. So there the DSP will come into the picture. We will put advanced FPGAs on board, and based on the user demand, we can reconfigure the satellite. So satellite reconfigurability is now nowadays state of the art. So how much flexible your satellite is, that is the basically state of the art your satellite is. Okay? Sometimes the satellite will be used for internet purpose, same satellite will use for the video conferencing purpose, same satellite can you use for the broadcasting purpose. So satellite will have now multiple role, although the satellite is same only thing what we are doing it, you can reconfigure the satellite for the various applications. So that is only possible once you are using this DSP or FPGAs inside on the onboard design. So I will show you some state of the art satellite technology globally, plus what ISRO is doing right now. So if you see right now, everybody I think at home has a DTS service set-up boxes are there, where you can see the Tata Sky or any other. So that is called Digital Video Broadcasting Standard. Currently India is having a digital video standard 2, DVB-S2. So what is the means is that that the uplink is from the like Tata Stars, they are having their own hub. They uplink their programs through RCS channel, through the satellite, and downlink to the users is in S domain. So the first standards comes is called DVB-S, but nowadays in India it's DVB-S2, DVB Digital Video Standard 2. So this is basically downlink. But the problem is earlier satellite, this is totally decoupled with the, means the RCS channels, first they go to hub, and then from hub all the programs will bunch together, again it will uplink to the satellite, and then they go for the broadcasting. So there is a 2 hop delay. First the like G networks will send all the programs to the hub, and then where all the other network player will club together, and then it will go to the satellite, and then from satellite it will go to the broadcast mode. So there is a 2 hop delay. But nowadays, if you want to use internet through satellite, 2 hop delay is not desirable, because IP based applications require 0 latency, almost nil latency. So if you go this type of architecture, it will not support internet through satellite. So what we have to do, we have to go hubless type of things, where the satellite intelligence is sitting, hub is sitting inside the satellite itself, so that all the switching, routing will be done on the satellite itself. There is no ground hub is there. Okay? So that is called advanced regenerative architecture in the satellite. So we are also working on this direction. In fact, few satellites we have launched. So that is the current state of the art. One change I can tell you right now, nowadays in set-top box you say video on demand. So what you have to do, like suppose you have a Tata Sky subscriber, with your registered mobile you can put request to the Tata Sky services that I want this movie, I will going to pay 60 rupees or 70 rupees. But that is happening through your mobile network, through GSM network. That is not happening through satellite. But suppose in villager, they want movie on demand, they don't have, because they don't have a GSM network. Correct? They have a satellite broadcast, because satellite broadcast is independent of area where you are, either you in Hyderabad or in village, doesn't matter. But the return link from user to satellite is through GSM network. But in this case, what happens, the return link is also through satellite. So either user is sitting in Hyderabad or in village, they can send through their terminal direct to the satellite, and satellite will recognize that it is a valid user requesting some movie on demand, and that will come down. So that service is already there in Europe, but in India now also we are going ahead with this type of design, that is called regenerative architecture. So as same way what we are mentioning, that initially the user has to send all the data to hub and then hub to broadcast. So that is called 2 hop delay. So in order to reduce this hop delay, we are going with the onboard processing type of things, where there is no hub sitting inside, and all this data will directly from terminal to terminal. So in Indian scenario, we have a few satellites which has been launched. So this is called a GSAT-4 satellite. This has launched I think 15 years back. This is a Ka-band satellite, where we have across the India 8 beams are there. So within the beam, beam to beam, all the communication is possible without any hub. So this is the first India regenerative satellite, GSAT-4 satellite, where it is in Ka-band, and it has a 8 beam satellites. Some advanced system, this is the internal payload architecture. You can see that any user want to send the data, he has to first send through request to the satellite that I want to transmit the data. It will go through a signaling channel, and then each channel, the channel is allocated to that user, and then he can start transmitting the data. So this is the architecture about that satellite. So some advanced system which we have developed for this satellite, this is called a signaling channel demodulator. This is the DSP based, ADI DSP based demodulator, which we have developed with, for this satellite. One multi-carrier demodulator, means what is the meaning of multi-carrier demodulator? Means single demodulator will able to demodulate 8 narrowband carriers. 8 individual users will transmit their data using QPSK modulation or APSK modulation. Single demodulator will demodulate all 8 carriers together. So how they are doing it? They have a 2-stage of demodulation. First, they do the demuxing, means all the carriers which are coming, they will put in that common IF, and then common IF will pass through a demodulator card where the data demodulation will happen. So there we have used all the advanced DSP techniques. This is called a polyphase DFT processing. I can show you some detail. This is the architecture. So if you see this, we are using multi-rate single processing concept, polyphase DFT approach to do the data demodulation. So this way we have developed the complete demodulation. I am not going in algorithm design, all this, otherwise it altogether different lecture, but I am showing what technology, what we are using it. So this is basically called as a multi-rate single processing concept, where without doing it RF domain, We down convert all the data at common IF, and from common IF we do the data demodulation using multi-rate concept. Okay. So this is one part. This is the payload photographs once it is ready. So this is complete hardware snapshot for 8-beam hardware. So this is called a satellite panel. You can downside you see that this is the satellite panel which integrate with the spacecraft, and that is type of harness routing we are doing it. The next satellite which launch is called INSAT 3DR. You know that ISRO trying to accommodate more number of applications in the single satellite. So this satellite is basically used for the meteorological application. This has been whatever the weather forecasting we are seeing, that this is being used by this satellite. Plus another application what we are trying to use is for the fishermen's, suppose they are stuck in sea, they can send their alerts signal to the terminal so that they are stuck somewhere in the sea, and then the rescue operation can be on. So that is called DRT application. So for that we required a digital filter on board to design, to basically curtail that fisherman requirement. If you see the specification of this filter, you can see what is so great on design a digital filter. But if you see this filter specification, basically if you see the transition band, it's roughly 20 kilohertz. And you know that in digital filter, the filter order is depend upon your transition band. So if you compute using MATLAB tool or any FDA tool, the filter order will come 15,000 tap filter. Okay. So any device you use in the world, they will not accommodate this 15,000 tap FIR filter in your design. Okay. So what we have done it, in order to reduce the tab order and all these things, we gone for a multi-rate FIR approach, which is called a multi-stage FIR implementation. So this 15,000 tab filter we reduce by design in 500 tab filter only. Okay. So these are some advanced signal processing concept we can utilize, that is called a multi-stage FIR filter approach. So that we have used it to design the filter, and this hardware, the right hand side you can see the realized response, you can see the brick wall type of response. So no other filter will give you apart from digital filter of this type of response. So this satellite is already flown and the working is performance is all okay. The next recently, I think down the line 6 months back, we have another replaced satellite of INSAT 3D. INSAT 3D, 3DR and 3DS. There are 3 meteorological satellites. 3D is almost completing its 15 years. So we have to replace the 3D satellite. So we launched the 3DS satellite. The earlier satellite which I discussed about the digital filter, this is on Vertex 4 design. So we have used Vertex 4 for the design of the digital filter. But once the satellite reach in the space, we found some radiation issue with the Vertex 4. We need to sometime do the reset in the design. Sometimes it get failed in the operational stage. So we don't want to face same issue again with the new satellite, since this satellite is totally new. So what we have decided to change our design approach. So why I am putting this thing, we also sometimes do reveal based on experience on board to change our design. So as I mentioned that in FPGA, the best FPGA technique is anti-fuse based. There we didn't impact with the environmental condition. So same filter which is flown in INSAT 3DR, we migrate to the new design where our design is based on RTX 4000 bit. It's anti-fuse FPGA. And here if you can see the whole logic is running at 284 megahertz clock. But we also, as in digital, what happens if you increase your clock speed, your design reliability will get reduced. So try to put your design at lower clock if it is possible. Sometimes by design it is not possible, but sometimes if you are able to do at lower clock, your design reliability will increase. Okay. So here what happens, the whole design is running on 284 megahertz clock, but later on we same design will try, we have put it at 50 megahertz only. So it's 284 versus 50 megahertz the thing. But you can see, sir, how it is possible that your earlier design with Vertex 4 is running at 284 megahertz. Suddenly we are using anti-fuse and with 50 megahertz. So we used Nyquist aliasing approach. You know that once you are doing ADC samples, they are not only the original image will come, some Nyquist image will also come. So what we are doing it, we are doing the band pass sampling at the ADC end. So we do 50 megahertz band pass sampling and try to capture the second or third Nyquist zone and try to capture that image. And similarly at DAC side also, DAC also give you the different Nyquist zone. So instead of using the primary zone, we are trying to capture fourth or fifth Nyquist zone. So using some advanced algorithms, we basically try to reduce our system clock design so that my reliability should increase. So that way we migrated from 284 Vertex 4 design to the RTX 4000 50 megahertz design, and this performance is very good and the design reliability is increased 4 times at least, I can say. Another concept we have flown is called GSAT 17 satellite. where on demand, as I mentioned that nowadays the demand is keep on changing. Now the user is demanding, sir, through command I want to change the filter bandwidth, gain, everything. Well, it is, can you provide that service? So we are ready with that. So this satellite is already in the, for the defense user, where the filter bandwidth is through command you can change to 1 megahertz, 2 megahertz, 3 megahertz, 4, whatever you want, is bandwidth will change, its frequency will change, center frequency will change, everything will be programmable. So this is like a SDR sitting on board. So that way we have put on board, and this is flown in GSAT 17 satellite. As I mentioned, the next is our that DVB-S2, Digital Video Broadcasting Standard 2. So there, if your idea is that all the RCS channel will club together at onboard itself and come to the downlink. So this also we have now proven in terms of concept. If you see, if you go to the ETSI standard, this, if you want to go in detail of that design, there is a called ETSI standard for digital video broadcasting. So this is the S2 implementation diagram. You don't get scared about this, because a lot of processing need to be done in order to make any packet as per the DVB-S2 compliant. So all this need to be implemented once you are basically want to transmit any DVB-S2 signal to the satellite. The idea behind the DVB-S2 standard is, it's from packet to packet you can change the modulation and code rate. Means your Tata Sky set-top box, if you, it's a DVB-S2 compliance modems. So if you send either QPSK rate half or 8 PSK next packet, or it automatically recognizes the modulation and code rate, and accordingly it will demodulate. So sometime what happens, your hub player want to accommodate more channels, so they will go for more advanced modulation, where the lesser bandwidth they can accommodate more number of channels, like HD channels. No? Suppose now HD channels are coming, but the transponder bandwidth is fixed. So how will you accommodate? You have to go with more advanced modulation to accommodate in the same channel more number of channels. So packet to packet you can change the modulation and code rate. So we also done some simulation on that side, and these IPs we have transferred to the industry for whomsoever we wanted to build. So all these technologies, IPs are available through InSpace. Anybody who want to do some development on the DVB-S2 side, they can take our IPs through InSpace. Another trend is nowadays is called a high throughput satellites. High throughput satellites is basically, till now the satellite throughput means how much data rate satellite can handle it in 5 to 6 Gbps. But nowadays the demand is more than 100 Gbps. So that is called a high throughput satellite, where satellite throughput will be around less than, should not be less than 50 Gbps. So that is called a high throughput satellite. So high throughput satellites, if you go through in the detail, this is our earlier days satellite in 60s, where all the RF translation is happening in IF domain, and the RF switching is happening. No? So all are analogous in nature, nothing is flexibility is there, everything is done. So the antenna will cover, LNA is there, then down conversion, then the RF switching will happen, and then the up conversion will happen. This is the traditional satellite. But nowadays what happens, this channelization is happening in digital domain. So what we, since you have to do in digital domain, we required A to D at front end. So that signal will come into digital domain, do some channelization in digital domain. Digital domain channelization benefit it, your granularity will increase. RF is fixed switching, but digital you can have infinite switching in principle. So that is happening, and then D2A, and then. If you go beyond also, what happens nowadays, these satellites are now coexisting with 5G, and later on 6G will also come into the picture. So lot of interference will come into the picture. So we have to create nulls in some area where the interference coming on. So in order to create nulls, we have to put digital beam forming network on the satellite itself, where the satellite itself will create some nulls at certain angle and create where you want to transmit the signal. So this also is now the requirement, and we are also using polyphase DFT filters to create the beam forming. If you want more advanced, further advancement on the satellite, then what happens, up till now the upcoming signal are not decoupled with the downlink signal. So what happens, the uplink noise is also getting coupled, and it will go through the downlink. So your downlink signal C by N naught is slightly poorer. So in real satellite and small antenna, we want to that uplink and downlink should be decoupled. Then what need to do, we need to demodulate the data at baseband level on the satellite itself. So uplink noise is decoupled, and then based on the user demand, what waveform it wants, we can again remodulate the data on board itself and try to transmit in the downlink side. So this is the advanced structure where academia can work. Right now we are also working in this direction. The problem with this type of design, the huge power requirement, because so many things we need to develop on board, and the power requirement is very hungry. So there are some novel algorithms, some novel concept will come into the picture, and this is nowadays open architecture where people can work on that. So we do some For the students, these are some advanced verification technique where they can utilize limited resources, but they can still verify their design. One is called FPGA in loop verification. This is basically given by the MATLAB team, where you have your own HDL design and you don't have any source and sink hardware is with you. What you can do, you have only Simulink and model sim for the verification. What you can do, your HDL code can come into the Simulink environment itself, and through in the closed loop itself you can verify your HDL code without having a FPGA board itself. Okay? So, this we are having now a standard practice that is called FPGA in loop, where some codes is in Verilog or VHDL domain, some modules in Simulink domain, they are together integrated, and closed loop you can verify the design. So, that is called FPGA in loop verification. Second is called HDL board itself. Although the code will be verified, but you, sir, I want to verify in the hardware board itself. That is called FIL, where what happens, your FPGA board also come into the Simulink environment, where we can download your own HDL code, put the FPGA board inside the Simulink environment together. So, where some blocks, like in this case, we are verifying turbo code, encoder and decoder. So, encoder is running inside the FPGA board itself, and the decoder is in Simulink environment, but we are verifying the HDL encoder implementation in the Simulink environment itself. So, this is the advantage of this type of approach is that without having a source and sink, because MATLAB have n number of source and sink, we don't, and channel models are there, noise source is there, we don't have to buy the physical hardware for that. That validation you can do in the Simulink environment. Only thing you require for this type of one FPGA kit, that's it, and plus the licensing of this. Otherwise, you will get everything free of cost. And you can have n number of source, you can have your own custom source, you can have n number of model, channel models you want to behave, because for each channel model you require separate hardware, but here you can get in a single environment. So, that is also some standard practice. Right now we are doing it, and I can recommend that you can also utilize this type of things. Navigation satellite, as I mentioned that we have some other branches also. So, up till now we have talked about the communication satellite, but if you ask me the navigation satellite, we have called a Navig satellite. So, there we built a Navig satellite. So, there are a few important subsystems, I'll just go through quickly. One is called atomic clock monitoring unit. This system is earlier we are procuring from Switzerland company, and only company in the world who is delivering this project, but now we have developed indigenously this system. The goal of this ACMU unit to monitor the rubidium atomic clock behavior and convert 10 megahertz from 10.23 megahertz. So, this hardware is developed in my division, where the input is 2 atomic clocks and output is 10.23 megahertz of Navig payload, where everything is running. So, this is the internal diagram of the ACMU which we have developed. This is the phase meter and controller card where all the designs is sitting. This is the package typically which has been flown in Navig satellite. Second is called navigation signal generation unit. Basically, this is I can call as a mind of any Navig satellite, where all the navigation parameters has been generated on board, and this has been transmitted through the modulators. So, this we have designed using RTG4 based design. So, inside the RTG4 itself we have a Leon 3 FT processor sitting. As I mentioned that we try to put more number of processor inside the FPGA itself if the design is possible to feasible. So, here we have put Leon 3 FT processor inside this RTG4, and this complete design is using RTG4. And these are the some parameters which we try to implement inside this is a complete design flow of the RTG4. This is the card with RTG4 based design which has been flown in Navig satellite. This is called a navigation signal generation unit. Digital modulators, this is now a very important, this technology we have transferred to even Indian industry now. This is a good part. Actually, now you know that in Navig we have 3 bands, L1, L5 and S band. So, this is like a SDR design where it is independent of frequency. You can configure it on board either for L1, L5 or S. This is a common design, and any modulation from ground itself you can configure. So, this is the SDR, and the concept is basically it's a 0 IF based design. So, all the modulation happening in 0 IF, and based on your command it can configure in L5 band, L1 band and S band. It's a common design approach. This is the internal flow of the modulator. This is the snapshot of the FM realize which has been flown in Navig satellite. Another important subsystem of Navig satellite is the atomic clock. You know the importance of the atomic clock, because this is the only responsible for you giving the sub-centimeter level of accuracy on the ground. Okay? So, earlier we are used to procure this clock from Spectra Time in Switzerland, and a single atomic clock cost you around 10 CR rupees. single clock. But now we have developed in-house, and now it is ISRO intellectual property. We have developed in-house this clock, and these are the internal details. I am not going in detail, we don't have a time, but I am just showing you the various design parameters of the clock. These are the few block sets which have been used in the clock. These are the some packages which are integrated inside the atomic clock. So that many package. The critical package is the cavity package where the rubidium transition is happening, and because of that only we get the pure clock of 10 megahertz. So this is the type of stability we get from this atomic clock. The green one is the specification line where we need to supposed to meet, but we are meeting with much margin. And this is the onboard data which I am showing you, the atomic clock stability, what we are getting it. So now it's a complete make in India now, this clock, and now from last satellite itself we have started sending our own clocks. So this has been now realized. Apart from that, as I mentioned, that the third arm is remote sensing, where we are using DSP and VLSI. So we have two counterparts on that. One is called optical remote sensing, another is called microwave remote sensing. So both have some merits and demerits. Where the cloud is there, optical remote sensing will not work. So suppose you have a weather monitoring satellite in optical domain, it will not see inside if cloud is there. But the microwave satellites can see that part. But the problem is the microwave imaging, they will give you a black and white picture, but optical imaging satellite give you the color picture. So there is some pros and cons in both. So we want both, because sometimes we require a color picture, we cannot differentiate in the black and white. And nobody in this world now will very happy to see the black and white image, they want a color image. So nowadays what happens, we are trying to put both the payloads in the single satellite, so that once we got sometime cloud is there, we can manage with the black and white image, but cloud is not there, we want a color image. So both the payload nowadays sitting on the single satellite. Some advanced packages which we develop for for remote sensing satellite is called a scatterometer. This payload is for the basically used for the sea wave monitoring. Sea has sometimes very rough sea is there. So sea wave monitoring is there. For that, this payload has been flown in SCATSat and OceanSat satellites. So this is the vertex based design, and this is the package snapshot. So basically inside this is the algorithm which we have implemented using Vertex 4. So where we do the sampling and multi-rate processing and capture the data in SNR. Two important missions like Chandrayaan 2 and Chandrayaan 3, where we have used lot of Vertex 5 and FPGA, that also I will go through that. Many people will not happy with Chandrayaan 2, but if you ask any ISROians, they will say that the most complicated payload is Chandrayaan 2. Although the Chandrayaan 3 has got success and we will celebrate Chandrayaan 3, but for us the most complicated payload is Chandrayaan 2, and very people not knowing that some part of Chandrayaan 2 is still working orbiter, and with the help of orbiter only the Chandrayaan 3 has got success. Okay, so it's the heaviest Chandrayaan satellite I can say, and but it got less appreciation because it's not landed successfully. Okay, but that part is hardly 10%, 90% satellite is got full success on that side. So it has as I mentioned, it has a 3-part: orbiter, lander, and rover. No? And this is the satellite configuration. So in terms of satellite configuration, if you see, this is the heaviest satellite configuration. Even Chandrayaan 3 is the lightest. Additional thing what we have put it with Chandrayaan 3, instead of orbiter, extra fuel we are carrying. So that if you have a more than one hour time to reattempt the landing, we can do that. But here the payload is there. There the fuel is there in Chandrayaan 3. Here we send the complete orbiter. Okay, so that is the difference. And there also we have a remote sensing. We have a 2-band of remote sensing, one in L band and S band. So that is called a synthetic aperture radar payload, which is there on board for the Chandrayaan 2. And if you see compare the technology what we have flown in Chandrayaan 2 with the international scenario, internationally nobody has sent this dual band synthetic aperture radar. We have the first one who can in the moon, we have sent the L and S band, where if you see mostly people have sent in S band only. Okay, so just I am giving you the comparison of what type of technology we have sent it. And if you see the SAR specification, why dual band is required? Because sometime what happens, the imaging in L band will not give you the good pictures. If you have a dual band frequencies or SAR, the data processing and data visualization will be more accurate. Okay, so we want to land more precise, then preferred is the dual band radar, SAR payload. So that is there inside. And the design is basically, the signal processing system is basically to have the imaging of the image. Now you know that in Earth, suppose you want to land a spacecraft, you have a GPS, BDU, Galileo, but in moon nothing is there. No? So how to land in the moon and where we have to land? So what we have developed, the technology I will tell you the layman, we basically taken the area where we want to land and put some small images and store in the onboard hardware itself. And once our spacecraft is nearby, we try to take the photograph instant and try to match in onboard store images where this thing is matching. And once we got the matching area and doubly sure that the image is perfectly matched, then we find out that this is the landing spot where we are trying to land. So this whole algorithm is sitting in this DSP domain, where we stored all the onboard images, and then once the real scenario comes, it try to compute with the scenario. So that is done using Vertex 4 devices. These are the various filtering stages, and these are the specifications which we have implemented. Some onboard range processing also we have done it using Vertex 4 design. So, so this is basically Vertex 4 which is flown in Chandrayaan 2. But in Chandrayaan 3, Vertex 4 is little bit prone to the sensitivity with the environmental condition. So this is just an image which we capture from onboard camera and then trying to compute onboard what images we have stored. So if there is a crater, the image will tell you there is a crater, don't land there. No? So that type of onboard decision autonomous is there. And particularly in South Pole, what happened, it is not directly visible to Earth. So the satellite has to take autonomous decision. So we cannot command them, no, don't land here. So he has to just take the image, see whether there is a crater, okay, we cannot land it here, move further here. So this autonomous algorithm is implemented on board. So there it is basically taking the decision based on the own decision. We are just a viewer. What spacecraft is doing, we are just seeing with the telemetry, nothing is in our control. Okay, so similarly, if you can see that this type of polarimetry images is been captured from the moon surface itself, and based on that we try to area where the craters are there. So there we should avoid for the landing. So that type of things are there. Okay, so this is the just the same thing, only different objectives I am just putting you. So this is the basically in this digital processor we have three things. One is this image processing thing, another is the called carb and altimeter is there. What is the role of altimeter? Once it is near to the moon surface, altimeter basically give you how much height is remain, how much you are. So accordingly you can adjust your velocity. And what happens, earlier the spacecraft is coming in the horizontal domain, and it has to zero down its horizontal velocity to 0, and then later on its vertical velocity will go in 0. So this altimeter will try to help you to find out the height, how far from the height of you from the moon surface. So all these things is also done using DSPs only in the FPGA itself, where we basically try to see the reflected signal and capture how much height is there. So these all the internal design is there. So all these three things are implemented in the Vertex 4 design, Vertex 5 design. So now this is the internal design of Chandrayaan 3, where we divided into 3 FPGA based design, 2 FPGA plus 1 ASIC, where the altimeter part is in 1 FPGA, another part where we are doing this image processing thing, and the third part where we all control segment is sitting together. So all this together in a single board we have designed it, although we have put a reliability, same card replica is there, main and redundant. So that's why we are this time confident, even one everything is failed, then also the second card will pull on, and immediately there should not be any failure. Here in Chandrayaan 2 we have one such card, and there is a software bug in that, and that's why we didn't take a decision at right time. Here what happens, such 2 cards are sitting there, they are working independently. So once it fails, then also the second will take over of that. So this is now the new design which is flown in Chandrayaan 3. This is the Vertex 5 based design, and all these commands are there. This I will skip. So this is actually, you can see that this type of samples we are captured, and this type of image we are storing on site. And then once our real satellites come, we will try to capture the image and see where we are. Okay. So you can see that we have identified the areas where basically the landing site is there. So some images which we captured on that day, I am just showing to that part. One video is there, I want to show the real video, whether it will play or not, just check, na? It is there. Where the actual camera house look like, it is not coming in for the public domain, but so I thought let me show you something which is internal to us. You just see that some video is there. If you click it here, not coming, no problem, So basically this camera is basically try to see the moon images, and it is a real time image which is capturing the moon surface and how our algorithms is play in parallel. So that's the snapshot. Anyhow, the video I don't know why it is not, no problem. Okay, so what is our near future? See, many people will ask the question with us, sir, why we gone to the moon? No? India is a poor country, people are getting 80 crores people are getting free ration, and you are investing in R&D without any mean. That's a valid question. Let me, many people ask me in some seminars and presentation. See, the effect of Chandrayaan-3, I can tell you, we got the success. Within 15 days, Japan approaches us, sir, we want a joint Chandrayaan mission with you. 50% share is yours, 50% is ours. Earlier, once India is proposing to work with any nation, no, everybody hesitates. No, sir, you do your own, we will do our own. Even during the Pokhran this atomic bomb explosion, even we didn't get any component from outside. So that type of restriction is put on us. But once we showcase our technology, countries like Japan, USA, Russia, France, they want, sir, we should have a joint mission together. So what happens, if you invest certain things, amount in technology will have an enormous return. Mission like Chandrayaan, we cannot do n number of times our own budget. No? Because such a mission, why space station is financing by 29 countries. Now India is also part of that. Why? Because a single country cannot, even the country like USA cannot afford to maintain that type of. So this type of missions like Venus mission I am asking, that Saturn mission in future we are planning. So India cannot afford that standalone, that be very clear, because we have other priorities in our country. But at the same time we cannot stop the science to develop. We cannot stop because our young population are so energetic. If you not guide them in the right direction, they will misguide, they will do something else. And 90% I can tell you that right now the young generation are migrating towards the software, because that is easy. Python programming, you learn it, everything will get a salary handsome and do that. But whether the inclination is science is going down now, and we have a requirement in the country where we need to develop our own technologies. We should not depend on outside world for the technology development. So these missions basically open as a gateway, that we have the capability, and country like Japan, now we have a tie-up for the next moon mission. So similarly, another mission which is very beautiful mission is coming in maybe in the next 6 months. You can see the launch, that is called NISR launch. So this is joint mission by NASA and ISRO. So half the satellite payload is developed by NASA, half the satellite is developed by USA. So before Chandrayaan, nobody is willing to work with us for this type of satellite. So they develop half payload, they send us to us their payload, and that payload is now integrated with our payload in Bangalore. Now the satellite is ready. Next GSLV launch is this only. So it's the first, I can say, NASA-ISRO collaboration satellite, where there are 2 bands of synthetic aperture radar. One is an L band and one is S band. L band is developed by ISRO. L band is developed by NASA, and S band is by ISRO. Okay? So it's a joint development. It's a very beautiful satellite, and it will create enormous amount of data for the researchers to do the analysis across the globe, even for the climatic change, even for all things. So this type of technology, satellites, why it is possible now? Because mission like Mars, mission like Chandrayaan-3 success is give us the opportunity to interface with the advanced space agencies like NASA, ESA or JAXA. Okay? So that is the thing. So the question comes, why we are spending the money? The spending money is required to have an interface with others, because in future missions we want to reduce our budget. Nowadays, if you see the space policy, we are basically trying to offload to the private company. ISRO is now only focusing on the advanced R&Ds. Why? Because we want to give the business to the private companies, so they should flourish, and plus the return means the job scenarios also increase, particularly in technology domain. Okay? So that is the thing. So my request is, do invest in this domain, do invest in science technology, because this is a very fascinating world. As a ISRO, I can say we always got thrill once our subsystem is designed by us, is flown in the space and work beautifully. No? So that is the basically the most satisfied, I can say, for us, that our design subsystem work beautifully on board. Okay? So that way, that's why we are investing in the foreign this advanced R&Ds. Okay? So this is the satellite where one part of the payload we are developing it, another part is developed by NASA. So this is our, I can say, the trend where we have. Apart from that, we have now 3-4 very good tie-ups. As I mentioned, Chandrayaan 4 is already approved, but that we are going to do alone. It's the biggest mission where we need to collect the moon samples at various places and return back to the Earth. So the satellite is such a big, in the single rocket we cannot accommodate. So we are going to launch 3 rockets. 3 payload will go together, they will integrate on board itself, and then they will go for the moon, they will land at 3-4 places, collect the sample, and one of the thing will come back and return to the Earth. So that is the overall mission profile for Chandrayaan 4. One mission with Japan we are doing it, where again the rocket is from Japan, half payload is from our side, it will go to the moon, do some meaningful experiment for more than 180 days, and then collect all the information and again return back. So that is also approved by government now. Venus missions, where we going for the Venus mission, they are also now lot of, once we announce the missions, like NASA, JAXA, they are approaching to us, sir, why don't you put us on board also, so that we can also put our instrument there. You came to know that in Chandrayaan 1, the first mission to the moon, we found the water on the moon surface. The instrument is from the NASA, but the satellite is from the ISRO. Okay? So they put us their instrument on board with us. So similar type of international collaboration is nowadays is true. And we have to do that because standalone we cannot do that. Okay? But there are certain applications where we didn't want any collaboration. Mission like Navik satellites, where the half the satellite is used by the defense users. No? So there the defense secrecy has to be maintained. So we cannot share their design. So there only the half portion we are putting in the public domain, half portion we are not declaring anything. So right now Navik has been very beautifully used by defense, but for the public domain, people will appreciate once Navik chip come in the mobile. So very soon you will see the Navik chip inside the mobile, and then you will appreciate that, yes sir, with Navik our position is getting improved better than GPS. Okay? So that is the thing, and that is our motto. And for the ground system development, the chip development, now government is investing huge amount of money. There are a lot of startups are coming who are developing the Navik chips at the ground, and we required crores receiver at the ground. Satellite is there, but in order to utilize satellite properly, we required different type of receiver, different quantity of receivers also. Okay? So please invest, a lot of investment is, startups are there who are coming for this development, and all of you I am requesting you kindly do insert your all mind there also to develop more number of chips, more number of fab labs are coming inside the India. You know that in Gujarat also we have Tata now started our own fab labs. They are giving 2 years free training to Singapore, and then you come for the fabrication, start working on the fab lab. Micron is invested, other companies are also investing. So we have a huge requirement. We want our dependency should be, outside world should be removed, and we should having self-sufficient in some sub technology and chip design. So that's all from my side. I just giving you some snapshots of this there. My mail ID is there. Anybody is interested in particularly doing something in VLSI, particularly in ISRO projects, if they want any information or anything, they can contact me on my phone or mobile, official mobile. I can, whatever the knowledge, whatever the detail I have, I can happy to share. But my request is kindly take, this is the transforming India. We are now, the target is to having a self-sufficient in all domain. Few domains we have now the mastery, but few domains still the pending where the huge quantity requirement is there. But we need to catch up, and we are, I think we are in the right direction. Thank you.
And this is Dr. Ram. Actually, I'm a startup from Malaysia, sir. I actually would like to know more on international collaboration, particularly in the satellite industry with Malaysia and ecosystem of ASEAN countries. Is there anything ongoing effort is happening, or I would like to pursue it further if something is open to startups like me to collaborate with Malaysia universities or bring some bridge between these two.
Actually, if you know that in 2019,
yes,
our
sir.
Prime Minister announced satellite for South Asian regions. No? That satellite, basically we have put this on the ISRO website. Any South Asian nations who wanted to do certain application with the satellite, they can send their proposal. Accordingly, we'll make a payload.
Yes,
so we got the proposal from few countries like Bangladesh, Sri Lanka, Bhutan, but I didn't know whether the country like there we got any proposal. Accordingly, we make one satellite, and that is called very soon. I think next year we are planning to launch that satellite.
So, University Science Malaysia, one of the research university where I graduated from PhD, they are looking for their nano satellite to launch. And
so that nowadays it's a very much now current government has regularized very beautifully.
Yes,
You
sir.
have to contact InSpace or NSIL. For nano satellite, I think you can contact InSpace. There is a separate part of ISRO team, those who are handling our external interfaces.
Okay.
So any satellite, like lot of startups is now, even some colleges nowadays making a satellite.
Yes, sir.
So they want like launch like PSLV. We have a capacity to put in some small satellites with some bigger satellites.
Okay.
So there, if you put a request properly, there is a form for that. If you wish, you can drop me, I can share you the form.
That
You
will
can
be great.
fill the form,
Yes, sir.
and based on the launch capacity,
Yes, sir.
they can fit you in some PSLV launch.
They have some non-disclosure agreement before.
Yeah. Lot of things had to be done. Your orbit has to be known.
Yes, sir.
Whether that rocket is going on that orbit, whether how much payload mass is there, everything will be required. But that will take roughly 3 to 4 months, and then based on the PSLV launch dates, we'll get one PSLV for that.
Okay, great, sir. And for the audience purpose, many people are launching satellites, and there are a lot of scrap is there in the space, right? What is the ISRO activities to clean the space?
Yeah, very
Thank
good
you.
question. Actually, very good question. See, globally, NASA is doing, basically I can say one institute is there who's monitoring, we call it space debris, okay. So, they are monitoring, and in fact, sometimes you see the launches, even in the ISRO launches, we give the time 4:21 launch time, and we say that launch is delayed by 2 minutes. Why this 2-minute delay comes? Because once we monitor this debris, we thought that once we launch this rocket, this debris will come on our launch profile, it might collide with our rocket. So we delay by 2 minutes based on the debris. So as you mentioned is correct. What happens, it's an international commitment for all the whomsoever is making the satellite, that once the satellite life is over, they have to deorbit them, and there is a orbit defined that is called a garbage orbit, where you need to park like a car parking. You have to park your satellite there, so that it will be not harm to other. But as I mentioned that everybody want dil mange more. So they want to last fuel of the satellite to use to the nation, because it's a very costly affair. So nobody will follow that order. So ultimately what happens, the satellite, and once every fuel is finished, they say, sir, we cannot move the satellite because there is no fuel. And nobody will go in the space to catch the satellite and put in the parking orbit. In car, we can have a tolling and we can toll the car but in satellite it does not happen. So similarly what happens, now very strong rules are coming through the international coordination, because these are now affecting to the working satellites. So that's the problem. The real image which at the time of Chandrayaan 3 is landing is there. This is the real image, this is not a video. This is a camera 4 we have on board, which is captured the moon landing in the South Pole. So in Chandrayaan, we have defined a very large geographical area for the landing. In Chandrayaan 2, we have a very small area. So that has created some, so this time we have identified very huge area for the landing. So anywhere it can be landed. Now the onboard camera and the roller, see this is the panel deployment once land. So this all process is automatic, it's commandable. This is the landing time, the solar dust has come out once you landed. That is now a Shiv Shakti point. India is now its own organization within the ISRO that is called Solar Debris Management, and we have just started. Its center is in Sriharikota, SHAR, where we have a whole station is there, where all the debris management we have started. Earlier actually in NASA it is a paid service. Once you are launching any satellite or any information, you have to pay to the agency. But now we are developing our own. So it is now become operational now. So we are not required now the NASA support for that. We have our own debris management program where we are monitoring, trying to monitor all the. But as you mentioned is correct. Globally now the various space agencies are mutually agreed that we have to launch such missions which will basically responsibility to clear the garbage, space garbage. But now it's quite huge, I can say you.
Is there any mentoring international collaboration is possible, paid or is also okay?
I think my suggestion first you contact InSpace.
Sure, sir.
Put me in CC. If some InSpace is in my campus only.
Okay.
InSpace headquarter and my ISRO campus is in the same area.
Okay, sir.
So I can talk to there whether right now it, as I mentioned that it is now for the Indian region.
Yeah,
Indian
that's what
startups.
I mean.
But they can consider based on the request.
Thank you, sir.
Excuse me, sir. Good morning. I am Usha from VNR College. I basically want to know what is the difference, how NAVIC is different or better than GPS. That is one question. And second question is, I am very much interested in it, and how as a student I can contribute in that aspect in working towards NAVIC.
Both are very great questions. First, congratulations to your great questions. See, once I say that NAVIC give you the better accuracy to GPS, there is a technical reason behind it. GPS is global coverage and NAVIC is for the regional coverage. The major error, there is a called position error budget. No? So GPS you will get sub-meter accuracy like 4 meter, 5 meter, and NAVIC I am claiming that sub-centimeter. Why it is so? Because in Indian region the most error budget is coming from the ionospheric, okay, ionospheric correction. So in GPS they don't have a whole globe ionospheric model. It's not possible, correct? So they basically on board they are using Klobuchar like coefficient for ionospheric correction. So that correction is basically model for particular region. For Indian region it is not so valid. So that's why in Indian region we will not get a better position accuracy because the error budget is huge. In India, what we are doing in NAVIC, we are not using Klobuchar coefficients. We are basically going to grid-based modeling of ionospheric whole Indian region. No? So what happens 5 kilometer by 5 kilometer area, we divided whole Indian region, and that there is a station sitting there, and that station is sending information to our hub, and from there we collect all Indian region information, and through satellite it is getting all the user receivers. So we will be having the local ionospheric information. So that's why our error budget is less, and that's why my position is better. So that is the main reason that we have a grid-based ionospheric correction. That's why the NAVIC position for the Indian region. But remember, GPS is for the global and NAVIC is for the regional. But I am happy to announce you that government has approved to NAVIC go for the global also. So maybe down the line 5 years, we have now MEO NAVIC cancellations. We are already the project approval stage. So once it is approved, the NAVIC will go in the MEO orbit, and now then we will call as a MEO global NAVIC cancellation. So NAVIC will also planning to go for the global coverage. But right now, yes, we are in regional region plus 1500 kilometers across the Indian region. And why we are having a better accuracy? Because we have a ionospheric local correction factor, which is not there in case of GPS. That is one part. Second part, as a student, what you can do? See, as a ISRO, we build the satellite, but the better receiver designs are there. And these receiver are going to use in practical life, where the practical interference will come into the picture, like multipath come into the picture, local ionospheric will come into the picture, tropospheric error. So student can understand the local requirement, and based on that they can participate in the modeling of the atmosphere. They can design the better multipath algorithms which can implemented inside the receiver for the better accuracy, because receiver is moving, na? So it has to face the multipath environment. So there the actual true test of the receiver will come into the picture. So there we can work on lot of algorithms design for the multipath, better ionospheric modeling, plus in the NAVIC we are keep on adding more signals. There you can participate in more signal design. So that way lot of opportunities are there. Plus as I mentioned, the chip design. So the idea is to design a chip with minimum power and minimum size. So whether the novel design, novel concept, VLSI concept you can apply to design the better NAVIC receiver, or the global GNSS receiver where NAVIC is also one channel.
Of digital filter regarding memory based or lookup table based?
That is a good question. For onboard, we'll prefer a lookup table based. But in general, depend upon the resource utilization, what type of filter is. Suppose you have a very high tap filter.
FIR filter.
FIR filter, I am talking about very high. Let's say I mentioned that in digital filter, we have a 1500 type of filter. Suppose you have such a high order of filter, then memory based will not do the job. Then you have to go with a LUT based approach. Then it will solve your issues.
And what type of storage element is used in satellites?
We have a Honeywell SRAMs are there, no? And these are the patented memories we use for, as I mentioned that commercial market is different, space market is different. So we have a very restricted type of components which we use typically. Right now the SRAM what we used for onboard NAVIC memory storage, we have used Honeywell SRAMs. These are their own patented, it's proprietary for them, for the, that's called space qualified memories.
Those are Indian origin or?
No, not Indian. But I wish some Indian should come with more better SRAM design which we can put it on the space. That's why this space policy, government has opened that more innovative chip design should come in future, where our dependency on the, right now only one dependency is pending as far as the space business is concerned. Some good components like Vertex FPGAs or memories, still we are dependent on foreign vendors. So that we want to reduce now.
Thank you for the wonderful session, sir. This is very generalized question, non-technical. So what, as a faculty, we have faced a few situations like our students mostly, as universities now have inculcated this internship concepts. It's a must and should concept for the students. And we are a failure in that, like we are unable to guide our students to run in these wonderful topics. Like today we got very good inspiration, many students have shown their interest. Now if you want to go to fill up this gap, to gain the career in this FPGA field, VLSI field, satellite field, somewhere is ISRO providing some breakages to fill up these gaps through startup internships or something?
So there are two answers for this question.
Sir.
One is, as I mentioned, that InSpace is now taking care of all the startups. Suppose you don't have any facility and you want to build a nano satellite or micro satellite, you can use the InSpace facility, even ISRO facility, and develop, and it's sometime based on the institute financial condition, they can provide you free of cost also, depend upon the things. So that is one part. Apart from that, as personal capacity, right now, as you mentioned is correct, right now the industry requirement is different and academic level, student level is different. So we have to somehow bridge this gap. Yeah. So as a personal level, what we are doing it right now, few professors from IITs plus MathWorks and we made a national wise basically committee. We are floating some courses which institute can opt, where some industry experts will participate to have a semester level course, which will basically we are trying to bridge the gap, and that course is not just once we design it is remain for 20 years. What we are wish is that every year based on how the industry moves, we will do some necessary changes in the content, and this is not only the theoretical study, hands-on is very important. Yes. So that course is basically theory plus practical. And we laid down all the necessary requirement what industry is supposed to be having a ECE engineer or VLSI engineer. If they having these courses, they will be certified by us, and so then they have additional skill. Skill is important. Yes, you should have a skill to get the job. That is the main thing. The skill set is missing. So we are right now on the, I can say the phase 1 of that. Very soon we are going to release a website where all this content or course design structure will be there. Any college who want to take this course, they can apply for that. It's not very costly, let me very clear. It's very nominal we are trying to put. And sometime even we are planning to do some workshop where faculty member can itself participate and learn the game, and they need not to call to us, and they can directly teach their student, motivating towards that part.
We will be desperately waiting for that situation.
So that will take roughly 1 year. 1 year down the line, I can share you the details very soon. We are already on the job. We have already started the course design. Right now we are for signal processing and communication, we are designing it. Later on our plan is to go for the VLSI also.
Thank you very much.
Hello sir, I am Sai Prakash, studying here, Embedded Systems and VLSI. So I was actually intrigued by something. Okay, we are doing it only for the scale of India. We are dividing it into grids, but this is still a very larger area, right? you put the satellite in the space and then you scan for our Indian subcontinent. I was interested in knowing how do we test this in a prototype? Like, जो सोच के रखा है, what is in the mind is actually very huge. So how do we actually test it on a prototype so that हाँ ये काम करेगा?
You need to contact our expert. See, just let me give you the snapshot. One school in Ahmedabad that is called Sanskar Dham. The principal of that school is Modi ji, our Prime Minister. Later on, once he become Prime Minister, that has been given to some trust. Their students from class 12, they are making right now some nano satellite. So they build something, and there is very small concept. They want to just see the light one satellite pass through their college school. They try to see some LED bulbs, and they wanted to see that whether the LED bulb is glowing or not. That much concept they want to prove in class 12. But the problem is they are not sure. That's like you. Whether sir the bulb jalega, मैं देख पाऊंगा कि नहीं, ना? So they came to us, कि sir please guide us. So we are right now helping them. They are structurally, what we initially found that their structure of the satellite itself is unstable. So once we release from the rocket, it is keep on tumbling. So we asked them how you will ensure that your satellite will be stable. So हमने तो सोचा ही नहीं था. So then we started to put them in the proper direction that we need to put some magnets, so and then the north-south pole stabilization, what typically do for the smaller satellite. Similarly, how much light you need to put it that should be visible from the earth. Okay, so they don't have any idea. So we have a simulation tool. We help them so that how that much luminance, if you blown from the space from that kilometer, it will be visible from the ground, and you can celebrate once this pass through your school or something. So that also we are not now giving them the guidance. So they are now ready, and most likely in May PSL will launch. They are this small. You can see in the newspaper that Sanskar Dham small satellite. Although the name will come the students, but the backbone we are doing helping them.
Understood, sir. That's fantastic.
Sir, continuation to what you said previously. So you told like India is also planning to extend the NAVIC into MEO, like for the worldwide. So basically we came down to NAVIC just because of the accuracy of that, the radius of the area is getting reduced, so precision will be more. So when again if NAVIC is extending itself to worldwide, then the same problem of the much area will be covered. So if the same problem occurs for GPS as well.
No. If you see China navigation, that is called a BIDU. So they have a regional constellation as well as the global constellation. So we are not stopping the regional constellation. So
Okay.
GeoCS satellite will be there.
Okay.
So Indian region, like in India, you will get a special food, and outside you will get a average food. So that is
Got
the
it.
idea.
Sure, thank you.
Thank you for the session, sir. Actually, this is Vinod, Osmania University, studying here. My question is actually, from India, how many satellites are launched up to now, and how many became as a garbage? Is the first question. And second question is how many years it will stay, the satellite? What is its lifetime?
How many in the garbage officially I cannot tell because we are also have some culprit of some satellite which we is supposed to park in the orbit, but as I mentioned, last fuel we are trying to utilize. So that answer I will not give you. But in terms of satellite, roughly around, if you include foreign launch, roughly around 464 satellite till now launch. Geo satellites are there for 15 years. LEO satellite mostly for 5 years. MEO satellite roughly for 7 years. What is your question again? Can you repeat?
How many years that's?
So the GEO satellite roughly just like NAVIC type of satellite, they are there for at least 15 years, GEO orbit. LEO satellite typically, because as you go lower down the orbit, your orbital correction will be more frequently because it will come into the gravity of the earth. No? So the satellite life is determined by the fuel of which is filled inside the satellite, because every time one satellite becomes deorbit, you need to fire the motor to again correct the orbit. So lower the orbit, more correction is required, so life is getting reduced. In GEO, once it is there, it will be very less correction because less drag is there, more vacuum is there, so orbit correction is required less, so they are there for at least for 15 years. But LEO, more near to more earth surface, more life is keep on reducing because more number of corrections is required.
Sir, then if the correction...
Again, coming to your question, as Madam mentioned my profile, I am a project director for the next satellite, which is called a technology demonstration satellite, which will launch in April time frame. There, because this satellite is very costly, as I mentioned that India could not afford such a costly launch. So what we are now doing it, like in car we have now electric car, so in propulsion system we have now electrical propulsion system. So in technology demonstration satellite we are now migrating from chemical propulsion to the electrical propulsion system. So that is called EPS system. So this satellite where I am the project director, we are trying to launch a satellite with the electrical propulsion system. So in principle till now the solar panel will having generating the power, that much satellite life is there. So typically our roughly estimation around 30 years or more than 30 years satellite life will be. So most of the countries now, just like in car, similarly in satellite, people are migrating towards the electrical because sunlight is abundant, only we need to utilize that part.
So just that if the connection is lost, we lost the satellite.
No. Once you don't have any fuel, satellite will be deorbit.
Yes.
So you don't have any signal control on that. So we declare that satellite is not in use because every satellite put in precise orbit for any particular applications. All the ground station are pointing towards that. But once the satellite leave that place, no ground station will able to track, and then time we declare the satellite is unusable to the country.
And the second question is, many satellites are also working for defense. So what security features we are giving for that compared to normal
I cannot answer few, but few things I can say. The defense satellite, once we launch, once we test the satellite is working, we hand it over to defense. Even we are not knowing what they are doing with the satellite. They have our own network, but primarily they have used some encryption on the top of the signal, which is not shared. Even the Navik, as I mentioned, the half satellite is shared by the defense. So once we launch the satellite, once we test the satellite in the orbit, everything is fine. The half satellite area is shared to the defense. They have their own management system in a separate place. Even very few, I think 1 or 2 people in ISRO knowing about what type of signal structure in fact they are transmitting. And they have their own encryption which is certified by their own agency. We are not involved in that. We are basically responsible for the civil signal which is for the general public.
Thank you, sir.
Okay, you can ask later, right? Another speaker is ready at 11:30. Thank you, Deepak ji.
Yeah, thank you, sir.
All the way you have come from Ahmedabad. In fact, Osmania University ECE department is always working in this navigational work. In fact, we have a Dept is another center we have. Even Osmania University ECE department, we started our journey with UGC project with USRP kits, capturing the data.
Okay.
And a GPS receiver standalone we have developed with FPGA. Without by removing the CPU, directly FPGA captures the real-time data and
Wonderful.
And we developed an SOC. That is the PhD work of Dr. Pradeep, who has done that work. And then we started our journey in the next level, Galileo satellite data. We are in CBI, that is tracking and acquisition. We are doing as a MathWorks project. We are doing. That is all MATLAB work we are doing, but maybe next level we may go for FPGA implementation also. And CTS project also is mainly objective is that self-sufficient. We should be self-driven. So this is a befitting lecture what you have given, because we are all proud and pride to be ISRO making Chandrayaan to be, to true. And even though we failed for 2 times, so fail makes us success. That's what the story we learned from Chandrayaan. So that is ISRO. We are all thankful and grateful to ISRO, and you are the person who are actually involved that, and then we are also proud of you. And thank you for your inspiring lecture. And you came forward to give your expertise to the next generation, which is we are looking forward. Osmania University also will take part of this particular course.
Yeah.
That is taking teaching or even for the learning also. We take the active part in our mission, so that that's what that even statutory bodies also are telling. So don't go conventionally, electronics, communication is all over. So how are the applications we can develop?
Yes.
Even 2 days back, Professor Ram Gopal Rao was also telling about sensors, agriculture and healthcare and all. Like
Yes,
this
yes.
also is another domain where ECE can become expertise. So finally, our dream is ECE is nowhere, less than other departments like computer science and all. So that's what our ambition and our aspiration. Thank you.
For the academicians, sir, one thing I just highlight. our ISRO every year launching a basket where what ISRO in future want to do with academia, that is called a respond basket. Last year it is 2023 it has launched, now the project has been distributed. This year again for the NAVIC type I am proposing 2 proposals and this is called Respond Basket 2024. It will be released in around 16 December or 17 December. It will be available on the ISRO website. You can see my name there in the basket. There are 2 proposals for the NAVIC. So I request academia, whomsoever is willing to participate in the basket, they have to send through proper channel the proposals. It will finally come to me. And last year for one NAVIC proposal, I got around 30 proposals record the Academia Institute. I selected one of them from NIT Trichy. But that is not stopping you. Right now this year also I am proposing 2 proposals for the NAVIC future design where the academia can come and participate. So I request the academia please come forward for that.
Respond to the response.
Yes.